All right, so last topic of the day is, and of this chapter, are greatest common multiples and, I didn't say that right, least common multiples and greatest common divisors. So we're going to take a look at, let's say, greatest common divisor first. And let's call them greatest common factors instead. And factor and divisor are used synonymously often. So just keep that in mind. So sometimes you'll see this abbreviated as GCF, other times it'll be abbreviated as GCD. And the way to think about this is, given some numbers, 2 or more, what is the greatest factor of all of them? So we're looking for factors of numbers. Those factors have to be common, and we want the greatest of the common factors. So we're just going to play around with that idea in a couple of different ways. And so the first way I want to do it is just with some simple toys, which are those color rods. Sometimes they're called Cuisenaire rods or color strips. All right. So remember, these are in order from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And sometimes classrooms will have sets of these so the kids can play around with them. So let's look at the greatest common factor of 1, 2, 3, 4, 5, 6 versus 4. And so what we want to do is find factors of 6 and 4. And so we know, for example, that 6 can factor as 2 groups of 3 or 3 groups of 2. Or as 6 groups of 1. Oops, what happened there? There we go. So this is our basic view here. Hopefully that color white is showing up on top of that light green grid. If we look at 4, we know that 4 can factor as 2 groups of 2. And when we put these toys together, they call them trains, right? So I just made a train of 2 reds. Or I could make a train of 4 whites, 4 groups of 1. So let me grab a screenshot of that so I can scribble on it. All right, got it. So we're just looking for the greatest common factor of 6 and 4. And so as far as common factors go, they have common factors of 1, the white, or 2, the red. And 2 happens to be the greatest of those common factors, right? So that's the simple way to look at it. And we can do that for any number. The bigger the number is, the harder it is to do with these toys. But with kids, we're just trying to get the basic idea with small numbers. And so we can make these trains. So similarly, instead of the toys, let's look at a bigger set of numbers for greatest common factor. Let's suppose we are checking out 12 and versus 18. In this case, we're not necessarily looking at prime factors, we're looking at any possible factor. And so the trick would be to list all factors of each. So that would be our factor pairs, 1 times 12, 2 times 6, 3 times 4, and we're done. 18 is 1 times 18, 2 times 9, 3 times 6, 4 doesn't work, 5 doesn't work, and then I get back to 6, so I'm done. And there are several common factors here, right? 1 is common, 2 is common, 3 is common, 6 is common, and let's see, 4 is not, 9 is not, neither is 12 or 18. And the greatest of those common factors is 6. Right? So looking at the list, it looks like 6 is the greatest common factor of 12 and 18. So we can look at lists of factors that way to figure it out. So another technique, so right now we have the toys to make trains of factors and see what's the biggest one, which is pretty similar as this numeric way. All the products I've listed here would be pretty much just like the trains I'm making here. So this picture here shows that 6 is 1 times 6, 6 is 2 times 3, and this one even goes farther to show 3 times 2 and 6 times 1. Right, so this is showing even more information than I was on the other page. So a picture version, numerical version. It turns out there is a way to find the greatest common factor using prime numbers. And we'll do a couple examples of this. So we're going to compare, again, 12 versus 18 again. And this time I'm going to make a factor tree because I'm doing a prime factorization. So in this case, I would start with 2 goes in there 6 times, and 2 goes into 6 3 times. So I can see that 12 is 2 squared times 3. And we do that for 18. So 18 is even, so 2 goes in 9 times, 9's odd, 3 goes in 3 times. So we can see that 18 is 2 times 3 squared. And again, what we're looking for is a greatest common factor. So I can only find things that are common, so that's kind of the thing we're going for here. So notice they both have 2 in common. But this one only has 1 2, but not 2. So when I'm coming down to identify what is the GCF, I can only use one of those 2's. Similarly, when I look at the 3, this one has a 3, that one has 2 3's, so I can only use the single 3 because it's got to be common. So I got another factor of 3. And then I get the answer, 2 times 3 is 6, is the greatest common factor of 12 and 18. So I'm going to repeat that procedure again. It takes a little bit of getting used to. So I can only choose common primes. Right, that's pretty much the strategy here. So we'll try it on a bigger pair of numbers. So greatest common factor of, how about 120 and 200. So we're going to do this by using the prime factorization again, see if we can piece it together. And we can also check by using the factor pairs. So we're going to use prime factorizations. So we need to make a factor tree for each number. So 120, and make yours any you like. Somebody have a question? Not at the moment. Okay. So let's see, 2 goes in there 60, 2 goes in there 30, 15, 3 times 5. So it looks like 120 is 2 cubed times 3 times 5. And then 200 and again, remember, there's many ways to make the tree. In the end, we list the results by taking the smallest prime first, which is 2, and there are 3 of them there, and then the next prime is 5, and there are 2 of them there. So there's the prime factorizations. Now, as far as common primes, we have 2 and 5 as common, but we can only take so many. So for example, both of these have, where's my pen? There you are. Both of these have a 2 cubed, oops, which is clearly common there. So when I write my GCF, let's go over here and write it, greatest common factor, I'm going to start listing the common factors. So clearly 2 cubed is common. The second one has no 3s. This one has 1 5, that one has 2, so the most they have in common is 5. So whatever 2 cubed times 5 is, which I think on a good day is 40. Yep, 8 times 5 is 40. So it looks like 40 is the greatest common factor there. To double check, we'll use the other technique where we list all of the factors and see what happens. So again, we're looking for the greatest common factor. And sometimes you'll see it abbreviated as parentheses, 120 comma 200. So that just says greatest common factor of 120 and 200. And this time we'll list all factors to find it. So 120 is 1 times 120, 2 times 60, 3 times 40, 4 times 30, 5 times 24, yep, 6 times 20, no 7, but we do have an 8 there, 8 times 15, I think, yep, 9, nope, 10, yes, 10 times 12, and then comes 11, and I am done. So there's all the factors there of 120. It's got a lot, almost as many as 360 had. And let's use a different color for 200. 1 times 200, and again, a calculator comes in handy. Sometimes I might move through this a little fast because I'm unfortunately too used to it. So feel free to say, yo, slow down, Parker. 3 doesn't work, 4 does work, 5 does work, 6 doesn't because 3 didn't, 7 doesn't, 8 does, 8 times what, 25? 9 doesn't, 10 clearly does, 10 times 20, 11, no, 12, no, 13, 14, 15, 16, 17, 18, 19, 20. I think that's the end of it. Did I miss anything?
It looks good. That's what I got.
I got them all. And whenever I'm unsure if I got them all, remember the trick I did earlier where I look at the prime factorization? For 200, where's my pen? We have 3 2's to choose from, so that gives me 4 ways to use the 2. There's 1 5, which gives me 2 ways to use the 5. 4 times 2 is 8. So there should be 8 factors total. 1, 2, oh, did I do something wrong there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, wait. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, what did I screw up there? 2 cubed. Oh, it's 2 cubed times 5 squared. I'm looking in the wrong spot. Okay, ignore that right there. 2 cubes, so 3 2s are not using, gives me 4 choices, times 2 plus 1 are 3 choices. 3 times 4 is 12 choices. Okay, there we go, that's right. Whew, scared myself there. It's like, where did I get all those extra factors? And then what we do is we look for all the common ones and pick the biggest. And so at first glance, it does seem to confirm that 40 is the biggest. I don't see anything bigger than 40. 50 doesn't work, 60 doesn't work, 100, 120. Yeah, so 40 is the biggest of the common factors. And there's a bunch of common factors. So we did confirm it here. So then you got to ask yourself, which one is easier, which one is more efficient? Now, easy kind of depends on one's experience, as does efficient. So I think, like, technically, computation-wise, this one requires the least amount of work once you get the system down. And so there's some homework problems you get to practice that with. All right, let's move on to lowest common multiple. And there's a few different techniques for approaching that. So least or lowest common multiple. Often abbreviated LCM. So breaking it down again, we're looking for multiples of a pair of numbers. Those, we have to have a common multiple, and we want the least, the lowest of the common multiples. So starting super easy with something like 2 versus 3. The most basic way to consider this is to actually list multiples for a while and see what happens. So multiples of 2 are 2, 4, 6, 8, 10, 12, 14. The question is, how far do you need to go? And the answer is as far as you need to. So I think I went more than far enough. They keep going. Multiples of 3, 3, 6, 9, 12, 15, and I can keep going forever and ever and ever. So I'm going to stop right there. And as far as, so we have multiples, right? We get that going. As far as common multiple goes, so let's circle those in red. Well, 6 is common. Next common one is 12 is common. And eventually I would have seen 16 and then 18. That 18 would have been another common multiple out here. So those are the common ones, but what I want is the least of the common multiples. And so definitely 6 is the least of the common multiples. So the LCM of 2 and 3 is 6. And a similar approach that we can take with the toys over here is, we can take our 2 block and start making a train with them. And the 2 is bigger, so I started off with, let's say, 2 of them, and I can see, okay, that doesn't quite line up, right? 1 doesn't line up, 2 of one of the other doesn't line up, and then I keep adding blocks until I can get them to line up. And there, I got them to line up. So here I have 3 groups of 2 and 2 groups of 3, so I can see 6 is the least common multiple. So the toys give a nice way to do it too. It's a slightly different way of using them than I did before. So let's try that for a different number. Like, let's suppose I wanted to compare 4 and 6 to see what would happen. So here's my 4 block right there. And here's my 6 block right here. And I can see, well, they don't line up. So then I start grabbing them one at a time, seeing if I can get them to line up, sticking end to end. And they still don't line up, but I think I might get lucky here. And they line up right there. So I can see 3 4s, whoa, get back there. Or 2 6s line up, which means 12 has to be the lowest common multiple. So again, those toys can give us a nice visual about how those multiples work, okay? So multiples are when we take multiple copies of that same number, 4, 4, and 4. So 12 is a multiple of 4. 6 and 6, so 12 is a multiple of 6. And the shortest train I can make where they both line up is the least common multiple, which is kind of cute. Now, the bigger the numbers, the harder this is going to be. So for example, let's try magic pen. There we are. The lowest common multiple of 12 and 18. And this is more of a problem for a lot of reasons, like multiples of 18 aren't down in my brain, right? I don't remember those, so I have to think harder about them. I'm gonna have to use a calculator to generate them probably. 12s, I get those down pretty good. So 12, 24, 36, 48, 60, 72, 84, 96, 108, 120, right? So multiples of 12, and they keep going. 18, now those I'm not as used to, so this is gonna be a little harder for me. 18, and 18 is 36. 36 and 18, okay, now here it's getting more challenging. That's what, 40, 54? Please help me out here if I screw up, or feel free to add a number for me. 54 and 18 is going to be 60, 72? Is that right? I think so. And I could keep going, but I'm going to stop because I'm starting to see some common multiples. So I see in common here, well, hey, 72 is common. And once I noticed that, I was wondering, wait a minute, is 36 common? Oh, there's 36. 54 wasn't. And I'm going to find that there's going to be lots of other common ones, and there's going to be a pattern to the way they happen. But I want the lowest of them, which I have here. And so it is 36. Come on, pen, change color for me. So 36 is the LCM. So let's look at another approach. And previously I was playing around with prime factorization, so I want to try that one again. And there's a strategy there too. So I want to find the LCM of, we'll stick with 12 and 18. So I'm going to use prime factorizations to do it. So we're going to make factor trees, the prime factorization technique. So only primes, 2 goes into 12, 6, 2 goes into 6, 3 times. So 12 is 2 squared times 3. And then 18 is 2 times 9, which is 3 times 3. So that one is 2 times 3 squared. And we did that, so hopefully that looks pretty familiar. Now, this time I'm trying to build a multiple, right? So again, what's our goal? We're trying to find a lowest common multiple. So if something is a multiple of 12, that means it has to be 12 times something else. And 12 happens to need all of those factors. 2 squared times 3 is 12. So when I'm building, so let's build the LCM has to have all of 12 in it, which is 2 squared times 3. So the first step here is to just use all the prime factors of one of the numbers. Let's call it the first number. Since we can't do things all at once, we have a first and we have a second. All right, so then I look at 18. Well, to be a multiple of 18, I have to have all of these factors in it. And so since I'm looking for common but lowest, I don't want to double count stuff, okay? So 18 says to me, it's speaking to me right now, it says, hey, Gary, I need a 2. And I say, 18, I got plenty of 2s, don't worry about it. 18 says, I need a couple 3s. And I can say, oh, well, I've got 1, I guess I can get you another. So I'm gonna switch color, there we go. That's not enough, I need a 3 squared here. Did I do it? Well, there's a couple ways to check. I could do the same process in reverse and see what happens. So let me try that. What if I start with 18? So build the LCM, starting with 18. 18 says I need a 2 times 3 squared. If you're my multiple, you got to have a 2 times 3 squared, because that's me. I'm 18. And then I look over to 12 and say, okay, 12, what do you need? And 12 says, I need a pair of 2s, please. And I look and I say, ooh, not quite there, but I am now. And then 18 says, I need a 3. And I say, I got plenty of 3s. Don't worry about it. Okay, and notice I got the same thing I have above. So whatever the result of this product is, so let's see, 2 squared is 4, 3 squared is 9, 4 times 9 is 36. So 36 has to be the LCM. Now, this, I think, is beautiful. So check this out. This blows me away every time I see it. What I want to do is I want to compare the LCM of 12 and 18 to the greatest common factor, the GCF of 12 and 18, by using their prime factorizations. So we know that 12 factors as 2 squared times 3. We did that a couple of times. And we know that 18 factors as 2 times 3 squared. When I built the LCM just now, we ended up, if we picked the 12 to start with, we ended up needing a whole 2 squared for the LCM. And we also ended up needing the 3 squared for the LCM. Okay, so I'm just going to say I grabbed that 2 squared and I grabbed that 3 squared. That right there is my 36, which is the LCM. For the GCD, or the GCF, well, I'm looking for greatest common factors, so factors that are common and take as much as I can that are common. That's important there. We ended up with just 2 times 3, which happened to be these other 2 right there. It's kind of interesting that in this case, we use up all of the factors here and here, but we redistribute them in different ways to get the LCM and the GCF. We're going to see if that works all the time. Okay, so I think there's a connection here. So we're going to test it again and then see if it really is true. So let's do another pair of numbers. Let's pick for our numbers. How about 21 and 35. No, 35 is too easy. $77. Okay. So we need a prime factorization for each of these, and then we'll go and find the GCF and the LCM. So prime factorization. Not too bad. They both have a pair of prime factors. So when I want to find the, let's say, greatest common factor, let's go back to that one right there. I need factors that are common, and it turns out the only thing common is a 7. Right? Just 1 7. LCM. Lowest common multiple, least common multiple. So that strategy, I need as many factors without repetition. So 21 says it needs a 3 times 7. 77 needs a 7 times 11, but I already have a 7 there, so I don't need to do it again. So I just need the 11. So one thing I could say here is that this 7 right here, let's say that's that one. And then this 3, 7, and 11, those are the other factors I didn't choose. So without repetition, if I take the factors of the original numbers and redistribute them, I can get the GCF and the LCM. Reminder, what's the strategy here? For the GCF, greatest common factor, what we're doing is choosing the lowest power of the common primes. So if we look back at the previous examples of this, we can double check that's true. So 7 is the only common prime, and it's to the first power, so it's just a 7. If I look back over here, the common primes were 2 and 3, and the lowest power of 3 was 3 to the first, the lowest power of 2 was 2 to the first, and those are the ones I ended up using for my GCF. Okay, so the GCF strategy, lowest power of common primes, if you have the prime factorization, right? You got to have the prime factorization. The LCM is a little greedier because it's looking for bigger stuff. So in this case, we want the highest power of all of the primes. So the primes present are 3, 7, and 11, and they all happen to be to the first power, so I need a 3 to the first, 7 first, 11 to the first. So highest power of all the primes we see here. If we double check that strategy on the previous example, all of the primes are 2s or 3s in this case, and the highest power was 2 squared, highest power was 3 squared. All right, so we got a couple different strategies for greatest common factor and lowest common multiple. I've got one more strategy, two more strategies, and then we're done. So we just took a look at finding the greatest common factor of two numbers. So let's say greatest common factor of A and B. And let's call that F because it's a factor. And we have lowest common multiple of two numbers like A and B. Let's call that M for multiple. And the interesting thing is the way they share the common prime factors, we get the following result is that if you take A and you multiply it by B, then you get the same thing as taking the GCF and multiplying it by the LCM. Right? So we could write that out more explicitly. A times B is the same thing as the GCF times the LCM. So if I'm better at finding, say, the LCM, then I can find that first, and I can treat this as an equation and divide the LCM to the other side. So I could write this as A times B divided by the LCM is always going to be equal to the GCF. And vice versa, if you're better at finding the GCF, then you just take A times B divided by the GCF, and that's always going to give you the LCM, which is kind of a cool result. So that's kind of another relationship there. And there's some homework problems you can test that out on. All right, last but not least, the next thing we're going to take a look at is what's called the Euclidean algorithm. For finding a greatest common factor. And it just involves a repeated division. And we've done algorithms before that involve some repeated division. And with the repeated division, we especially want to include the remainder in that. And I'll show you how. And so I'm just going to pick on 12 and 18 some more. We've had a bit of fun with them. So what you do is you take the two numbers you're looking for. So somebody says, hey, find me the GCF of 12 and 18. And my first step is to just divide them. So what happens if I take 12 into 18? So let's see, 12 goes into 18 once. 1 times 12 is 12. Subtract, I get 6 as a remainder. So then what I do is I take the 6 and the 12 and I do a division with those. So my next step is to say take 6 into 12 and do the division. 6 goes into 12 2 times. 2 times 6 is 12. The remainder is 0. And once you hit the 0 remainder, that says stop. 6 is the greatest common factor. Okay, so the last remainder, which is my last divisor, has to be the greatest common factor. And this works all the time. So I'm just going to pick another pair of numbers and have you help me out. So let's see, either in the chat or by voice, I need a couple of 2 or 3 digit numbers, please. Let's see, where is the chat?
117.
117, okay. And someone else?
436.
All right, and let's say I got 212. I'm not sure which happened first. So 117 and 212 is what we're going to do. All right, so new page. And we're going to need a calculator for this. So we're going to find the greatest common factor of 117 and 212. And we're going to do it first using the Euclid method, and then we'll try with the factoring method, for example, the prime factorization. So what I would do first is I would take 117 into 212. And actually, I don't even need a calculator for this, I don't think. I can see it goes in there once, but not twice, because if I double 117, I'm going to get 234, which is too big. So this goes in once, subtract, and what do we get? We get, I'm going to have to borrow kind of. 12 minus 7 is 5, 11 minus 2 is 9. Ooh, no, I did not do that right. This goes there. Oh man, I totally messed that up. Interesting. I was trying to do 2 different algorithms at once. 11 minus 1 is, okay, I'm going to start over. Maybe I do need a calculator. One more time. 117. Okay, so let's see. Oh, I did that right the first time. Oh no, I didn't. That's a 12. This becomes a 2. I'm using the equal additions algorithm. 12 minus 7 is 5. 1 minus 2 I can't do, so that becomes an 11. That becomes a 2. 11 minus 2 is 9. Okay, 95. So that's my remainder. So then I take 95 into 117. 95 goes into 117. Well, I can see it goes in once. Hopefully I can subtract better this time. 17 and 5 is what, 22 is the remainder there. And then I take 22 into 95. Okay, that's a bit more work. Let's see, 4 times 22 is 88. I think that's about as close as I'm going to get. And again, feel free to use a calculator anytime. 88 to 95 is 7. And then I just keep going until I get that 0 remainder, and then I know when to stop. So let's go down here. Hopefully I didn't make a mistake. 7 goes into 22. How many times? 3 times. Remainder 1. 1 goes into 7. 7 times. Finally I get a remainder of 0. So that means stop. Oops. Stop. And so the previous divisor or remainder has to be the answer. So it says the greatest common factor of 117 and 212 is 1. So the only other way we have to double check that is to use some other technique, and the next easiest technique to this one right here, and oftentimes this is an easy technique compared to others because prime factorizations can be really hard. So let's check the prime factorization. 117 versus 212. Let's see, 7, 8, 9. So 3 goes into 117. Let's see, 3 goes into 11. 3 times with 2 left over. 3 goes into 27 9 times, and which is 3 times 13. So this is 3 squared times 13. I was thinking 117 might be prime at first glance until I noticed that 7 plus 1 plus 1 is 9. 212, 2 plus 1 is 3 plus 2 is 5. 3 does not go into 212, but it's even. 2 does. So 106 times, still even. 53 times. And 53, I think, is prime, isn't it? Oh, ow, oh, sorry, attacked by a cat. Yeah, 53 is prime. So this is 2 squared times 53. Now they have no common primes, but every number has a factor of 1. So since there's no common primes, the greatest common factor has to be 1. By the way, when two numbers have no primes in common, they're said to be relatively prime to each other. So 117, 117, and 212. Stop, get away, cat. Are relatively prime. Sorry, it's dinner time for cats here, apparently. She's telling me to shut up. Talked enough about math. All right, so I think this is a good point for me to shut up. Okay.